Hello everyone, we are team number one.
And we still cannot find our team member for 2 months.
However, we will show you how to build and, OR, and not gates in the lab. Let's start.
Oh, really? We are starting the team project and you just broke the camera?
First, we connected the power supply to provide voltage to the circuit. Then we added our beautiful LED to show the output visually. The short leg of the LED was connected to the ground or negative terminal using a jumper wire. Next, we added a 330 ohm resistor to limit the current coming from the positive supply. This resistor protects the LED from burning out. Then we connected the long leg of the LED to the resistor. After that, we added the transistor, which is the main component that makes the inversion happen. We connected the collector of the transistor to the LED circuit. Then we connected the base of the transistor to a 2000 ohm resistor. This resistor controls the current going into the base. From there, we connected it to the push button. As you see, the push button is testing my patience. So it means that big things comes from small things. After all this, I added a jumper wire to finally complete the circuit. Finally, we connected the emitter of the transistor to the negative terminal to complete the circuit. At first, I connected the 330 ohm resistor to the negative side, but then I corrected it. As you see, mission completed successfully. Now, let's move to the explanation of NOT gate. Here we can see the NOT gate. On the left side, we have the input labeled A. This is where the signal enters the gate. In our lab, this input comes from the push button. When we press the button, we send the logic 1. When we release it, the input becomes 0. In the middle, we see the triangle symbol. This represents the inverter circuit. Now, look at the small circle at the output of triangle. It shows inversion, which means the signal is reversed. On the right side, we see the output labeled Y equals to A bar. This means that Y is the opposite of A. So, this gate always gives the opposite result of the input. That's why it's called the NOT gate. First, we connected the power supply. Then we added the LED. The short leg of the LED was connected to the negative terminal using a jumper wire. Next, we added a 330 ohm resistor to limit the current and connected the long leg of the LED to this resistor. From there, we used a jumper wire to connect the resistor to collector of the first transistor. Then we connected the emitter of that transistor to the negative terminal. After that, we connected the base of the transistor to another resistor using a jumper wire. We added the second and third transistors to create the AND logic. Their emitters and collectors were connected in series, so current can only flow when both transistors are activated. Then we added 2000 ohm resistors to the bases of second and third transistors and connected them to the push buttons. The push buttons were connected to the positive supply using jumper wires. one point, I accidentally connected the jumper wire to the second transistor's emitter out of muscle memory from the NOT gate, but I corrected it. Now, LED turns on only when both push buttons are pressed, which confirms the AND operation. Now, let's move to the explanation of AND gate. In this photo, you can see the AND gate. On the left side, there are two inputs labeled A and B. In our lab, this input comes from the two push buttons. Each button represents one input signal. In the middle, we see the AND gate symbol. Notice the left side is flat and the right side is curved. This shape represents the logical AND operation. On the right side, we see the output written as A.B. The dot between A and B means AND multiplication in digital logic. This means the output will be 1 only when both A and B are 1. If I press only one push button, nothing happens. The output stays 0. But when I press both buttons at the same time, the LED turns on. This happens because the switches are connected in series. So, current flows only when both paths are closed. That's why the AND gate requires both inputs to be true. First, we connected the power supply. Then we placed the LED. The short leg of the LED was connected to the negative terminal using a jumper wire. Next, we added a 330 ohm resistor to limit the current and attached the long leg of the LED to this resistor. A jumper wire was then used to connect the resistor to the collector of the first transistor. After that, we connected the emitter of the transistor to the negative terminal. The base of the transistor was connected to the 2000 ohm resistor using a jumper wire to prepare for the inputs. Then we added a second and third transistor to complete the OR logic. Their collectors were connected to the same resistor, and their emitters were connected to negative, allowing current to flow if any transistors receive input. Finally, we connected resistors to the bases of second and third transistor and linked them to push buttons. The other side of the push buttons was connected to the positive terminal using jumper wires. Now, the LED lights up when any of the push buttons are pressed, confirming the OR operation. Well, let's move to the explanation of OR gate. And finally, we have come to our last gate, which is OR. Here you can see the OR gate. On the left side, there are two inputs labeled A and B. In our lab, these inputs comes from two push buttons. Each button controls one input signal. In the middle, we see the OR gate symbol. Notice that the left side is curved inward. This curved shape represents the OR logic operation. On the right side, the input is written as Z equals to A plus B. In digital logic, the plus sign does not mean normal addition. It means OR operation. This means if input A is 1, the output becomes 1. If input B is 1, the output also becomes 1. And if both of them are 1, the input is still 1. The output is 0 only when both inputs are 0. In our experiment, when we press either push button, the LED turns on. That's because the switches are connected in parallel, so current can flow through either path.